All right. Okay. So I guess one thing I would do before we get started in the book would be to talk a little bit about Appendix F and the trig worksheet. Okay, if we could start with the trig worksheet maybe. Now, I don't want to spend a great deal of time here, but we could work one as an example. And then if you've got some questions on the trig stuff, because keep in mind, the next quiz may have a no calculator part, and any no calculator quiz from this point forward will assume that you know some of those basic graphs that we put in our notes the other day, and will assume that you can solve trig equations that involve 30, 60, 90, or pi 6, pi thirds, pi fours, or the angles that land right on the quadrants like pi halves and pi. Okay, so you need to be able to do that. So if you're struggling with that, the SOHCAHTOA thing or drawing triangles or whatever, be sure to come talk to me about that. So any questions on any of those? Those 8? I don't have the answers sitting here in front of me, or I'd read them, but just if there's any, otherwise I'll just pick one. All right, well let's look at number 7. Okay. Number 7 says 4 sine squared x times tangent x equals tangent x. Now, a few people asked me on this one about dividing by tangent on both sides. Okay? Now, the problem, trying to record this for a few people that are going to be gone. So the problem with dividing both sides by tangent is you cannot divide by 0. Right? That's illegal. Dividing by 0 would mess up the equation. So what happens then is we lose any solutions where tangent would equal 0. So as long as you're aware of that, that's okay. So in other words, you could say, well, I'm going to divide both sides by tangent, and that would give me 4 sine squared x equals 1, correct? All right, but we've lost potential solutions where tangent is 0, because think about it. If tangent is 0 right here, this side would be 0, and over here this side would be 0, and 0 equals 0. So any values where tangent is 0 are solutions to the original equation, but they might not be solutions to this. So what you would have to do is you'd have to say, okay, I have to also check for possible solutions where tangent is 0. So as long as you're aware of that, then that's okay. Now the other strategy is to subtract tangent to the other side. So you get 4 sine squared x tangent x minus tangent x equals 0. That's probably the one you're more comfortable with. And then do what? Factor out a tangent. So you take out a tangent, and then you have 4 sine squared of x minus 1 equals 0. And then what? You set each one of those equal to 0, and then you end up at the same place. Okay? So either one of those is okay. But a lot of times if you divide by something that could be 0, it gets you in trouble, because then you just forget about it. It's gone, and then you don't worry about it. That's not good. All right, so on this one, we go ahead and divide by 4. We square root both sides, which gives us plus or minus square root of 1/4. Well, that's what? 1/2. Okay? And then where is tangent 0? So now, let's deal with where tangent is 0 first. Tangent is sine over cosine. Now you could think of the tangent graph, but it's probably just as easy to think this. Well, where's a fraction ever 0? When the top is 0. We don't want the bottom to be 0, but the bottom, in this, comes back to natural domain. Cosine won't ever be 0 in this problem, because that makes tangent undefined, and tangent's in the original up here, so it would never be a solution when tangent's undefined anyway. Okay? So we don't have to worry about that. So we want to know when the top is 0. So we're really asking ourselves, when is sine 0? Well, now that goes either to the unit circle. Sine is the y coordinate on the unit circle. So y is 0 either there or there, which would be at 0, pi, 2 pi. What was our limits on number 7?
2 pi.
We did not include 2 pi, so because that's the same as 0. So 0 and pi, there's 2 of our solutions right there. Now I also could have graphed the sine graph and asked myself where sine equals 0, which is at 0 and at pi, and we said we weren't including 2 pi. So either one of those could have answered that question. All right, where does sine equal plus or minus 1/2? Well, plus or minus means what quadrant we in? All 4. So if you just remember, where does sine equal pi halves in the first quadrant? Pi over 6. If you don't remember that, you have to at least recognize that that's a 30-60 triangle. Remember the important ones. Square root of 2 over 2 is pi fourths, which is a 45-45, or 1/2 or square root of 3 over 2. If you see 1/2 or square root of 3 over 2, those are your 30-60s. Okay? So sine, if you don't have this memorized, sine is SOHCAHTOA, opposite over hypotenuse. So 1 over 2, opposite over hypotenuse. Across from the 1 is always the 30, which is pi 6. We're going to be in all 4 quadrants with a pi 6. Here's the thing that probably throws people off on these as much as anything is dealing with fractions. You got to be able to deal with fractions if you're going to do radians. Okay, we're in all 4 quadrants. Of course, one answer is going to be pi 6. Now, what is that? Well, I think the best way is to remember that this is pi over here. So therefore, since I'm dealing with 6 in this problem, I'm going to think of that as 6 pi 6. Because that's pi. This is 1 short of that. 5 pi 6. This one is 1 pi 6 past 6 pi 6. 7 pi 6. And then this one is 1 pi 6 short of 2 pi, but 2 pi is 12 pi 6. So 1 pi 6 short of that, 11 pi 6. So we got 4 solutions plus 2 solutions. We got 6 solutions to number 7. Okay? Now, later on, we will have, one of the things we'll talk about today, we're going to get started talking about derivative. And just so you understand why we want to be able to solve these kind of equations, either with a calculator or without a calculator. And that's because, very quick little scenario, we're going to be interested in max values of functions. And what is the slope? We've already talked, and we're going to talk today about derivative is the slope. What is the slope at a max value? 0. So we're going to learn about derivatives of functions, and if we're going to find the max, we're going to be looking for where is the derivative equals 0. So pretend that this function right here is the derivative function of the function we're trying to find the max of. We would find the derivative function, which there it is. We would set it equal to 0, and then to find where the maxes happen, or the mins, we have to solve that equation. So we do this all the time. Well, many times in here will you find an equation and set it equal to 0, and then have to solve it. Okay? And sometimes it'll be trig equations. So we got to be able to do it. All right. So that's the trig stuff. If you've got other questions about those and those triangles, then we'll deal with those at a later time. Let's take a look at the calculator and Appendix A. And problem, I think it was number 25. Is that the one that had the center a function? Was it 25? 25 and 29. All right. Okay, let's go to a calculator page here. A graph page on our calculators. And what was the graph cosine?
Yeah.
25 was cosine and 29 was 1 over x squared. Okay, 25 is cosine at 0, 1. So let's go ahead and graph the cosine graph. Did they give us a window? We're supposed to find the window. Centered at 0, 1. Okay. So that's, of course, this peak right here on the cosine graph. So if I go into the menu, into my window, some of these zooms you should get familiar with. Zoom trig is a pretty good one when you're dealing with a basic sine or cosine. What it does is it makes the markings, well, it looks like they go by 0.5. You get 6.28, which is 2 pi over there. But what I want to do, they want to find a window centered at 0, 1 so that this graph looks straight. Now we're kind of sneaking ahead into section 1.5 here a little bit. But the idea is, what we're going to be talking about is we want to know the slope. Now this is an easy one because the slope is what? At the point 0, 1. It's 0. It's a horizontal tangent line like the picture I just drew a minute ago. So that's pretty easy. But if we want to find that window where it looks straight there, it's like we want to take a microscope and we want to zoom in. Because if I was to draw, let me draw on here a second. Imagine this line being on here. Okay. So if I was to draw a tangent line, here's the idea. If we could zoom in with a microscope right there, okay, right at that point, wouldn't there be an area there where the red graph and the blue line basically overlapped each other? Now technically, the blue line is a tangent line, so it touches the graph how many times? It only touches the graph once, okay? But if we zoomed in with the microscope, at some point it would be so hard to tell the difference. The blue and the red would be so close together that you really couldn't tell the difference between it because you have to make the line thick enough to see, right? But technically they only touch at one point. So that's the idea here. And so we go ahead and what we'll do is we'll go into our window, we'll go to zoom in, okay? Now, when you go to zoom in, you get this little magnifying glass that asks for the center. Where do you want to zoom in at? Well, what you do is you just place that over top of where you want and click. Okay, just place it with your trackpad over that point and click. And then do it again. Then do it again. See what's happening? What we're doing is we're coming in there with the microscope. And keep doing it until it looks straight. Okay? Not quite yet. Now it looks pretty good. Okay, now this is still the cosine graph, but we're zoomed in so much, we're just looking at a teeny little piece of it like there, and it almost looks like a line. Of course, the idea is we could calculate this slope now. Of course, we know it's 0, but so a horizontal one's not that interesting. But we could now pick a couple points on the cosine curve that are really, really close. Remember, we did that very first day. We said pick 2 points really, really close to 0, right? We can pick 2 points on this cosine curve. They're not on that blue tangent line. They're on the curve, but they're darn close to being on the blue line, right? Okay? Because when we zoom in, we got that blue line. Now, it only touches at that one point. Okay? And we don't know any other points on that blue line. We only know that one, but we do know all the points on the cosine curve. So if I pick 2 points on the cosine curve really, really close there, they'd be really close to being on the blue line. So finding the slope between those 2 points would almost be like finding the slope of the blue line. That's the idea. Okay, and we'll be getting into that more tomorrow in section 1.5. Okay, so now they just said find a window. So at this point, you would just go to your menu, you'd go to your window settings, and you would just write those down. Right? You would just come over here and you would just say, use maybe brackets. And so different people would have different answers, but say, okay, for my x, I'd have negative 0.01285 to 0.01169. And my y would be 0.99228 to 1.0080. Okay, so if it says find a window, that's what it means. Give me an x min and max, give me a y min and max, where that curve looks straight. Okay? So that was what we were looking for. Okay. Let's go ahead and turn in our book then to page 36, 35, 36. All right. All right, there's a notation that we will be using this year for the derivative. Okay? F prime of x. Now sometimes we just write that as f prime and we just leave off the input variable because it doesn't really matter. We've talked about that. The input variable could be t or whatever. F prime of x. Don't write very well. All right? So f prime of x is the derivative of f of x. We can also think of it as the slope, or let's say slopes of f of x. We can also think of it as the instantaneous rate of change of f of x. Those are all saying the same thing. Okay? Now at the top of page 37, they've got a graph here, like so. And this is the position graph. And they've got a second graph over here. Try to copy, I wish I had. All right. Now, and this is the what? The velocity. And they talk about this car that is on the interstate at Bismarck, North Dakota. And for several hours, this car moves west and it moves east at various speeds. Now, time is in hours. That's the t-axis, okay? So position is different than distance in the sense that it can be negative. And same with velocity. Velocity, because that indicates direction. So think about an x-axis, okay? Think about Bismarck being the 0 on the x-axis. If we go to the east of Bismarck, that's a positive position. So if I go 10 miles east, pretend that's like standing on 10 on the x-axis, right? Just a number line now, not 2 dimensions, just think of a number line. We used to call it the x-axis, but just think back in middle school when you were dealing with number lines, right? So you're at 10. If you go west of Bismarck, okay, you're at negative values. So if you're 10 miles west, your position is at negative 10. So that's how come this position here goes down to negative. So when we talk about the position, the velocity values, we're always talking about the y value. That's why we spent the rest of time dealing with functions for this first quiz. Function values, we're talking about the outputs, okay? So, when does this cross here at 6? Right here is 6. So that means 6 hours later the car is where? Back in Bismarck. Where had it been? East of Bismarck. It had been east of Bismarck because its position is positive. Its position is above the x-axis. Now, we're going to start talking about slopes here in a minute, and then things start getting confusing. We got to be real careful saying it's positive. You know, what is it? Okay, and I'll do it myself. We got to be careful then. The position, the outputs of the position function are positive because they're above the x-axis. Since they're positive positions, they have to be east of Bismarck. Now, then he goes west of Bismarck, and then back at what, 8? He comes back. So at 8, he's back at Bismarck. Okay? Now, what do those points correspond to on the velocity graph? The 6 and the 8. Anything necessarily important on these graphs? Not necessarily, because all those mean, the only thing these two mean is he's back at Bismarck, right? They don't really talk about how fast he's going, right, when he gets back to Bismarck, okay? The only thing that I suppose might be important is that at 6, this one is down here somewhere. I think 6 is right around in here. So his velocity is negative. That means what? If his velocity is negative, he's going west, right? Velocity negative means he's going west. Well, that's true because coming back to this graph, what's going on at this graph at that time? What's this graph doing at 6 besides crossing the x-axis? Going, well, the graph is going west? The graph's going down at 6, right? The fact that the graph is decreasing, right, means he's going west. Because increasing position, think about it, think of that number line again. If I go 1 to 2 to 3 to 4, my position is increasing. That means I'm going west, or excuse me, east. But if my position goes from 6 to 5 to 4 to 3, my position is still positive, but it's decreasing. 6, 5, 4, 3, those are decreasing values. I'm going back to the west. So when this graph goes down, it means he's coming back to the west. Well, doesn't that correspond to when this one's negative? Where is this peak right here? At 3. What do you see over here at 3? Right there. Because to turn around, to change direction, you have to stop. Right? Now, you have to stop your eastward, westward, right? You make a U-turn and never really stop. But at some point, when you make a U-turn, you stop from going east and come back to going west, right? You have a little north-south in there when you make that U-turn, but we're ignoring that. We're only talking about the east-west movement. So before he can turn around and come back, he's got to stop. His velocity's got to be 0 for just that instant, okay? So this changes from positive to negative when this one changes from increasing to decreasing. Now think about how that relates to slope. Isn't that true? What are the slopes right here? Positive. We just got in saying that f prime is the slopes of the f graph. So these slopes are positive. These y values are positive. Then the slopes go negative all the way to this. What's this peak down here? Where's that at? About 6.5. My picture's not very good. But that peak should correspond to this one at about 6.5. Right? Again, these values are decreasing. Now there's two ways for values to be decreasing. Okay? There's two ways for values, numbers, to decrease. One way is to be positive. This is my own invention. I don't know if it makes any sense to you. If it does, use it. If not, ignore me. But one way to decrease is to have a positive number get less positive. 6, 5, 4, 3. That's decreasing, right? But negatives then gets a little trickier. To decrease as a negative number, that's what? -1, -2, -3, right? Those numbers are getting smaller, aren't they? -1, -2, -3. I say, when I do something like that, I think of negative and getting more negative. So, two ways to decrease. Positive and get less positive, or negative and get more negative. That's decreasing. Well, if you look at the graph, same thing. Right here you got values that would be, I don't even know what those are here, 50, 40, 30, 20, 10, it's decreasing. And then it gets down to here, -10, -20, -30, right? They're negative and getting more negative. They're going away from 0. Okay? Now down here you have negative values, right? So what do the negative values mean down right here where I'm pointing right now? But what about the car? No. Okay, listen carefully what I'm saying. The fact that this value right here on the position graph is negative means what? He's west of Bismarck. This value by itself doesn't say anything about what direction he's going. It just says he's west of Bismarck. What tells you that he's going a certain direction? The fact the graph's going up, right? The slope. Since the slope's positive, he's going in what direction? To the east, right? So he's west of Bismarck. Right here, he's west of Bismarck, but he's coming back to the east. He's coming back towards 0. Okay, he's to the left of the number on the number line, but he's coming back to the origin. Okay? All right. And look what we get over here. We get positive y values. That's because these slopes are positive. So positive velocities, again, means going east. Going east. Okay. So there's a lot going on here. Now, these are connected. This graph's called the P graph. I called that the V graph for velocity, but I could call it the P prime graph. Okay? Because that's what it is. The velocity is the rate of change of position. Okay? And we talked about this from day one. We talked about the door opening. And we said that was a derivative. The rate of change, the slope, was the derivative. Okay? This would be in miles. This one would be in miles per hour. That's the derivative, P prime. Okay? The derivative of position. So there's all kinds of things going on here. Now, what about the slopes of the velocity graph? What does it tell you that the velocity graph right over here is going up? His speed is, now we got to be careful when we start talking increasing, decreasing with velocity because we confuse it with speed. So we got, velocity has direction, so we got to be careful. But right here, that's why I picked velocity being positive right here. His velocity is increasing. His speed is increasing, which means he's going faster. What's the word for when your velocity changes? Acceleration. So the slope of this, the derivative of P prime, is P double prime. That would also be V prime. That's the derivative of the V function, the velocity function. And we also call it acceleration. So a rate function, that's what another term we use for derivative. A rate function can have its own rate. You can even have changing acceleration. But that one doesn't have quite the physical implications, so we don't deal with it very often. Could we have a third derivative, and a fourth derivative, fifth derivative? Absolutely. But we rarely do. First derivative and second derivative give us the most useful information in different various uses that we have for it. So that's most of what we study. Okay? So acceleration would be the slopes of this. Now, again, back to what I was saying, and again, we will work on this over a period of time if this whole, if west, east, direction, seems a little confusing, is hang in there and work with it. It's not something that just always comes right away. Well, I was saying that if I say to you my velocity is increasing, do you picture right away that I'm speeding up? Right? Don't you think? If somebody say, hey, my velocity is increasing, you think, hey, I'm speeding up. Well, it's not true all the time. Because right here on this graph, that's the velocity, right? Is that increasing? That's increasing, right? It's going up. The velocity graph is increasing. So right in this area right here, we say the velocity graph is increasing. Now what are those velocities doing? They're negative and getting less negative. So these would be speeds of like negative 50 mile an hour, negative 40 mile an hour. Now what's the negative mean? Going west. So he's going negative 50, then negative 40, then negative 30, then negative 20. What's he doing? Slowing down, right? He's slowing down. So to say the velocity is increasing does not necessarily mean speeding up. And that's why I think sometimes increasing, decreasing can get confusing. I think it's better here, if I'm talking about the velocity increasing, I'll say, how's it increasing? And what I mean by that is, it's either say it's negative and getting less negative, or say it's positive and getting more positive. Because those are the two ways numbers can increase. Negative and get less negative, or positive and get more positive. Okay? So another way to think about it is going towards zero. If your velocities are going towards zero, you got to be slowing down, right? Because the zero velocity is stop. Okay? So that's another way to think about that. All right. So this is we use position and velocity as our first example of derivative and rate of change because those are the most easily understood and the most common that we deal with. But we can have other rates of change, right? For example, there's talk right now with all the stuff going on in the economy and so forth, there's talk about inflation, right? And so price per ounce, that's a rate, right? So the rising of prices and things like that, those are all rates of change. So in business, if you're a business major, a lot of times you're going to have to take an applied calculus. They deal a lot with those kinds of applications of derivatives. We'll get into some of those later on too. All right, so we're going to think about slopes as two things. One is rate of change. In problems like this, we'll think about derivative as rate of change, okay? Because it makes a lot of sense when you're dealing with velocity kinds of questions. If we're dealing just with some graphs that we don't know what they represent, we'll talk about slope. So rate of change and slope will be kind of interchangeable, depending on what the problem is and which one makes the most sense at that time. Okay, turn to page 40. And if we look here, there's a picture on page 40 of these tangent lines. Now keep in mind, we've done some tangent line stuff already, and before the book, before we got into the book, so the authors, they think this is the first time you guys have seen this. But, they're talking there about, think of taillights on a car, or headlights on a car. So driving along this curved road and think about the tangent line being the headlights going off in that direction. Of course, it's zero there, negative slope here. So when we talk about the slope of a curve, slope of a function, what we really mean is the slope of the tangent line at that point. Okay, because slope really only makes sense with lines. Okay, so when we talk about slope of a curve, we really mean slope of the tangent line. All right, so that's kind of an important picture just to understand that business there. Page 41, two more important things to talk about here. On page 41, they give you a couple of equations that we need to probably just know, probably just memorize. All right, so we'll write these down. And these have to do with position and velocity as it involves free-falling objects, where the only thing affecting them is gravity. Okay? The first one is, so we'll use height. We'll use h as our function instead of p for position, because this is going to be free-falling things that are acted on by gravity. The equation for the height is h sub 0, which is the initial height, plus v sub 0 t. V sub 0 is the initial velocity. You want to jot that down. H sub 0 is the initial height. V sub 0 is the initial velocity. So if I throw something up in the air, the instant it leaves my hand, it's got an initial velocity, an initial height that it was thrown in. Okay? And then minus, and then depending on whether we're in feet or meters, it's either 16t squared or it's 4.9t squared. Okay? It's half of the acceleration of gravity. Okay, acceleration of gravity is 32 feet per second, or 9.8 meters per second. So it's half of that. So this one's for meters, and this one's for feet. All right? The velocity equation, which would be h prime now, okay, the velocity equation would be the same as h prime, the derivative, is equal to v sub 0, the initial velocity, minus either 32t or 9.8t, depending on which one you're doing, whether you're using feet or meters. And later on in chapter 2, we'll show where these come from, how these, came about. All right, so you will be asked some questions then. These are just some pretty famous, as far as position, velocity kinds of things, okay? Just anything that doesn't have any external force to it. So something that's dropped or something that's thrown up in the air. So you'll be asked some questions, kind of like on the first quiz where I expect you to be able to graph something and read values and solve and make sense of it. There's some problems that talk about throwing something off of the roof or whatever and asking you when will it be at its highest point, how fast is it going at this time, so forth, so on. You'll use these, you'll plug in the values they give you in the problem, and then you'll go from there. Okay? All right, so that's one thing. And then the last thing to do today is this. On page 42. Speed limit law. Okay? And we're going to actually write this out. Let f be a function defined for x in AB, that means in some closed interval AB, okay? And let m be any real number if f prime of x is less than or equal to m, for all x in AB, then f of b minus f of a is less than or equal to m times the quantity b minus a. Obviously, then you need to write it. Everybody knows that. Right? What does it look like? Spanish. Or Greek, or something. Latin. All right. So let's break this down. What does this say? Okay, first of all, what's f prime mean? Derivative, and what are the two different ways? Slope or rate of change. In this instance, slope would be the easier one to think about. Yeah, actually, we'll do it with both, slope or speed. We can think of it as speed like a rate of change. So let's think of it like a car moving, okay? So if I had a picture here of f, Okay, let's think about a car moving. So F would be its position, F prime would be its velocity. Okay? And we'll make it be positive the whole time so we don't have to worry about moving to being west or east of Bismarck. Now the speed, the velocity might go negative. It might change that. But let's just say we got this graph F. Okay? And here's A and here's B. So this would be F of A and this would be F of B. Right? Correct? So this would be its beginning position, and it drove for a while. Now what did the car do? It went which direction? Let's keep with the west-east thing. It's going east and then back west a little and then east a while more, then west, then back to the east. It ends up farther east than it started, right? Now, how far did it travel? F of B minus F of A is how far it traveled. Net distance traveled, right? It's net distance traveled because it did kind of go back and forth. But it started here and it ended here, so its net distance traveled is F of B minus F of A. Oh, that's that right there. Okay? So let me write that down. So net distance less than or equal to, now what's M? If F prime then is its speed, or velocity, right? Let's say velocity. If its velocity is less than or equal to M, what's that mean M is then? What would be a word or a phrase we could call M that would make sense here? If F prime, now remember F prime is its velocity, is less than or equal to M, there's a reason we chose M, by the way. It's max, right? That's the max speed, its limit, right? Its speed limit. That's the max speed it went. Because what this line right here says, if its velocity is always less than or equal to some number M, that's like saying this is the fastest it went. Okay? So that's its fastest rate. That's M. Times, and what's B minus A? Wouldn't that be the time? That's what this axis is here, is time. So this would be the time that it traveled. Correct? So as we start to think about what all these things mean, this is saying if the fastest it moved was M, then this is saying that its net distance has to be less than or equal to its fastest rate times the time. Now remember, rate is miles per hour, and time would be in hours, so wouldn't that give you miles? Yeah. Okay? They have a sentence right above there that says this. Let's put some actual numbers into it. So if I tell you that 60 is the fastest I went, if 60 is the fastest I went, and I did that for 2 hours, what do you know? The most that I went is 120 miles an hour. Right? And so this makes perfect sense.
It's just miles.
Miles, okay? So if the fastest I went is 60, then my distance traveled has to be less than or equal to 120. Right? If I went 60 the whole time, then I went 120. But if I slowed down at all, this is called the speed limit law. Now, that makes sense with rate. Let's make sense of it with slope. Now let's pretend that M is the slope. The steepest slope, right? Because it says my slopes, F prime is my slopes. This is saying my slopes are always less than or equal to some number M. Now remember, slope is rise over run, correct? Okay? So, if the steepest slope I ever have in my function is M, then this says F of B minus F of A. What could be another name for F of B minus F of A? No. F of B minus F of A is the rise, isn't it? So f of b minus f of a is like the rise. M is like the slope, which would be rise over run. And what's b minus a? The run. Rise over run times run should be rise. So what this is saying, let's put this in some actual numbers. Let's say that I tell you that the derivative is always less than or equal to 2. That's saying the slope is always 2 or less. That means every time I go over 1, the most the graph goes up is 2. Let me say it again. If I tell you that f prime of x is less than or equal to 2, that's like telling you the slopes are 2 or less. So every time I go over 1, the most I can go up is 2. Okay? So the run times the slope gives you the rise, right? So if this side is the max slope, then this should give you the max rise. Just like if this is the max speed, then rate times time should give you the max distance. That's all it's saying. So if max slope of 2, take that times the run, that's the most the graph could go up. Okay? So you'll be asked all kinds of questions about the speed limit law, but they essentially sound just like that. Okay? Let me give you a real simple one here.
The runs cancel out.
Yeah, the runs would cancel out and make right. Let me just show you what that means. So I'll say this. So write this down as an example. So if f prime of x, let's use the one we just did, is less than or equal to 2 for this particular function f. If f prime of x is less than or equal to 2, and f of 1 equals 4, okay, could f of 5 equal 15? That questions like that are the type that when you see them you think of the speed limit law. Okay? If f prime of x is less than or equal to 2 and f of 1 is equal to 4, could f of 5 equal 15? No. What's the most f of 5 could be? Because that could be another question. I think I've heard it. 12. Now, picture is very helpful here if you're not seeing it. F of 1 equals 4 is like drawing a point, right? F of 1 equals 4. What is this saying? The max slope is 2, right? The slope has to be less than or equal to 2. Now they're asking me about f of 5. So that means if I have a run of 4, is what that's saying, my max slope of 2 means the rise can be at most 8. So I don't know what this graph does in between here. It could actually go down because it just says the slope's less than or equal to 2. The slope could be negative. This graph could go down. But we know it can't go up more than 8 because if it went up more than 8, it'd have to have a slope greater than 2. And it says right here it doesn't. So if it goes up 8, that puts you at where? That puts you at an output of 12. So the most f of 5 could be would be 12. F of 5 could not be 15. That's the speed limit law. And what's important about that? Well, what's important about that is we'll find out later on is we're going to be very interested in what f prime can tell us about f. Well, that's like your speed telling you about how far you go. It makes sense that those two should go together. If you know how fast you're going, you should know something about how far you went. And that's essentially what the speed limit law is saying. If we know something about how fast we're going and the direction, then we'll know something about where we went and how far we went. Okay? All right. So that's the speed limit law. And you can see why understanding this notation and some of these problems we've done with reading the notation and know what it's saying are really important. All right. So your homework for tomorrow is the 1.4 homework questions. Hopefully some of them seem very easy, okay? But you'll make them harder than they are. Okay, like if let's take that car driving here for a second. And let me mention one more thing here. If we had position velocity of the car driving around Bismarck, and I just left these off. I should have written this down. If I write, this is that car now, hours and miles, driving east and west of Bismarck. If I write P of 2 equals 70, what is that saying? At 2 hours, 70 miles east of Bismarck, because it's positive. So you would, once again, I'll tell you a question that's going to be on the next quiz. It's going to be one like that. What does that mean? Give you a description, and you have to write what the notation means. At 2 hours, and that's key, at 2 hours. And if I tell you time started at noon, you'd want to say at 2 o'clock. He was 70 east of Bismarck. Now what if I say V of 2 equals negative 100? At 2 hours. Now forget this one. Okay, forget this first one. This one doesn't have anything to do with that one. This is a whole separate scenario. At 2 hours, 100 miles an hour to the west. This alone doesn't tell us if he was east or west of Bismarck, though, right? Now, if I put it in conjunction with this, right, we could do that. But this alone just tells me traveling to the west, because it's negative, at 100 miles per hour at 2 o'clock. What's P prime of 2 equals negative 100 mean? The same thing. Yes, the same thing. Velocity and P prime are the same thing. Okay? So those two, I could ask either one of those and you would say the same thing. He's traveling 100 miles an hour in the westward direction at 2 hours. Okay? So notation kinds of stuff. 1.4 homework questions. 4 more.